Hi everyone. So now we are going to study about magnitude comparator. So this is also an combination circuits. So what it will do, it will compare the magnitude of two binary numbers. So there will be two binary numbers. It could be of 1 bit, it could be of 2 bit, it could be of 3 bit, 4 bit, 5 bit. So two binary numbers will be compared. So this is the job of magnitude comparator. Okay. Now very basic thing we know. 1 is greater than 0. What is the magnitude of 1 1? That is 3. 3 is greater than 2, is greater than 1, is greater than 0. 7 is greater than 6, is greater than 5, greater than 4, 3, 2, 1 and 0, right? But let's observe something very interesting. Let's see these two numbers. Which is the MSB bit? This is the MSB bit. Here, this is the MSB bit. Now, if I look at only MSB bit, then if your MSB bit is greater, that means your number will be greater. Because here 1 is greater than 0, although 0 0 is less than 1 1, but if my MSB bit is greater, then my number will be certainly greater. Say yes or no. Let's see other example now. If your MSB bit, let's see these two examples. Here MSB bit is same. This is your MSB bit, this is also your MSB bit, both are same. Now where we will go? We will go to the second bit. This is the second bit, here this is the second bit. Here if second bit is greater, that means the number is greater. Although this bit is lesser than this one, 0 is lesser than 1, but if second bit is greater, then certainly the number is greater. Now if second bit is also equal, let's go to these two examples. Here 0 0 is also equal, 0 0 is also equal. Then we will see the third bit. If third bit is greater, that means the number will be greater. So how we need to start? We need to start from the beginning. If that bit is greater, then certainly the number is greater. If these two bits are equal, let's check here. This bit and this bit is equal, this bit and this bit is equal, but this bit is greater than 0, so certainly this number is greater. Now let's check these two numbers. This bit and this bit is equal. Now 1 is greater than 0, so certainly this number is greater. Now let's go to this number. 1 is equal, 0 is equal, but 1 is greater than 0, so this number is greater. So we need to check in this manner. First check the first bit, MSB bit, then go to the next. If that is greater, that means certainly the number is greater. Then go to the next, then certainly the number is greater. Right? So this intuition I will be using in our analysis. Okay. So we are not going to solve it using K maps, but with our intuition only we are able to write down the final expression, and that we will see in our lecture. So now we will see 1 bit magnitude comparator. So we will compare 1 bit. So this is your 1 bit magnitude comparator. If it is a comparator, that means there will be two input, no? This input is A, this input is B. Now A is of 1 bit, B is of 1 bit. This is what they mean. Two inputs are there, A is of 1 bit and B is of 1 bit. So they will say 1 bit magnitude comparator, but input will be 2 bits. 1 bit is of A, 1 bit is of B, right? And there will be 3 outputs. First one would be greater. Now greater can be defined as A greater than B as well and B greater than A as well, but I am defining greater as A greater than B. Okay. Second one will be equal, that I am defining as A is equals to B, and third one is lesser, that I am defining as A is lesser than B. It could be other way around as well, that greater could be B greater than A and lesser could be B less than A, but here I am defining in this manner, that greater is A greater than B, equal is equals to A equals to B, that would be 1 only, and less is A less than B. Okay. Now here let's check. A naught is 0, B naught is 0, both are equal, so this would be 1, these two will be 0. Here A naught is 0, B naught is 1, that means this will be 1 and these two will be 0, because B naught is greater here. Here B naught is greater. What about this? Here A naught is 1, B naught is 0, so A naught is greater here, and these two will be 0. What about this? A naught is 1, B naught is 1, both are equal, right? So what you can write? This is your greater, this is your equal, and this is your lesser. So what is the expression of greater? That is A naught, B naught bar. What is the expression of equal? This is simply XNOR gate, right? XNOR gate. You can see it is XNOR gate. And what is the expression of lesser? That is A naught bar, B naught. So these are the expressions we are getting. This we can easily make from our from logic gates. How will you make it? For greater, this is how you can make it. Inverter, and then there is a gate, and for these simply you can use an XNOR gate. and for this you can use another NAND gate. So basically A, B, A, B, A, B. Here you will get greater, here you will get equal, here you will get lesser. So just you pick that in a box and that would be your gate. Okay, that would be your combination circuit. But let's write down these expressions again with a very good intuition. So what I need to compare? A naught and B naught. I am writing greater. Greater, that means my A naught should be greater than B naught. If my A naught is greater than B naught, that means A has to be 1 and B has to be 0. Is there any other condition? If I want my A naught to be greater than B naught, that means A has to be 1 and B has to be 0. There is no other condition where A naught can be greater than B naught. So this is the only condition. So what I will write? A naught, B naught bar. If I need to write lesser, that means I want my B naught to be greater. If I want my B naught to be greater, that means B naught should be 1 and A naught should be 0. I want B naught to be 1 and A naught to be 0. I am writing SOP form, so A naught will be written in bar and B naught will be written in bar. Now if I write equal, for writing equal, when it can be equal? If A naught is 1 and B naught is 1, so A naught is 1 and B naught is 1, or if A naught is 0 and B naught is 0. A naught is 0 and B naught is 0. Let me tell it again. They can be equal when A naught is 1 and B naught is 1, or A naught is 0 and B naught is 0. Are you getting this point? Or and. So what is this? A naught XOR B naught. So in that manner you should also write down the values, okay, or the final expression. So in that manner also you should be comfortable writing your final expression. Let's see it for 2-bit magnitude comparator. So it is a 2-bit magnitude comparator. That means input will be 2 inputs only, but that input will be of 2 bits. So this is your input A, this is your input B, but A is of 2 bits. Basically your A is A1 A naught and your B is B1 B naught. You can take an example, that is 1 0, it could be 1 1, right? So this is the scene. 2-bit magnitude comparator. So input will be always 2. Input will be always 2, but this input is of 2 bits. 2 bits input is there. Okay. So again greater, equal and lesser. So again I am defining greater as A greater than B, equal as A is equals to B, and less as A less than B. Okay. You can make the truth table. If you make the truth table, how will you write the truth table? You will write in this manner: A1 A naught, B1 B naught, and then these answers G E L, right? So let's write down the truth table, but we are not going to solve it using K-maps. So for greater, A greater than B, A naught A1, B naught B1. So this is also 0, this is also 0. That means it is equal. What about this one? This is also 0, this is 0, this is 1. So A is greater than B, that means A is less than B. This is 0, this is 2, A is less than B. This is 0, this is 3, A is less than B. This is 1, this is 0, A greater than B. This is 1, this is also 1, both equal. This is 1, this is 2, A is less than B. This is 1, this is 3, A is less than B. Now this is 2, this is 0, greater. This is 2, this is 1, greater. This is 2 and this is also 2, equal. This is 2, this is 3, greater. Sorry, lesser. 3, 0, greater. 3, 1, greater. 3, 2, greater. 3, 3, equal. So these are the truth table. Now you can write down the final answer. Make the K-map and write down the final answer on your own. You can do it, but we are not going to solve it using K-map. So how we will solve it, that we will see. But before that, let's see an interesting observation. So if I am saying that I have 2-bit magnitude comparator, 2-bit magnitude comparator. If I have 2-bit magnitude comparator, then inputs will be 2, but each input will be of 2 bits. Each input will be of 2 bits. Magnitude comparator will always have 2 inputs. Let's take an example of 3-bit magnitude comparator, because 2-bit you can directly see. 3-bit magnitude comparator. So input will be 2 only, A and B, but this will be of 3 bits and this will also be of 3 bits. So how many bits are coming at the input? 6 bits are coming, right? So if I am writing n-bit magnitude comparator, that means how many bits are coming at the input? N-bit magnitude comparator. So each number A, let's just say A, it will be of n bit and B will also be of n bit. So 2n bit will be coming at the input. 2n bit at input. If 2n bits are coming at the input, then how much total combination will be there? If 4 bits are there, the total combination are 2 to the power 4, right? If 5 bits are there, combination are 2 to the power 5. If 2n bits are there, 2 to the power 2n total combination. Say yes or no? At the input side, you are having n plus n 2n bits. If you are having 2n bits, so these kind of total combination you can write 2 to the power 2n, right? Now out of these, 2 to the power n times you will get equal. 2 to the power n times you will get equal. And rest of the times, 2 to the power 2n minus 2 to the power n. So how much is left? 2 to the power 2n minus 2 to the power n. Half of this will be greater and half of this will be, I will explain it, no need to worry, and half of this will be lesser. Okay, how I am saying so? How many bits? Let's just say there is 2-bit magnitude comparator only. 2-bit magnitude comparator. So this is having 2 bits A0 A1 and this is having 2 bits which is B0 B1. When they will be equal? When both the bits are equal. That means A is 0 0, this is also 0 0. A0 is 0 1, this is also 0 1. 1 0 1 0 1 1 1 1. So basically we are taking total combination of A0 and A1. Say yes or no? What all are the possible combination of A0 and A1? At those times it will be equal. You can see here A0 0 0 is equals to 0 0 1 here, 0 1 is equals to 0 1 1 here, 1 0 is equals to 1 0 1 here, 1 1 is equals to 1 1. So total 4 times it is equal, and it was 2-bit magnitude comparator. So 2 to the power 2, total 4 times it was equal. It was 2-bit magnitude comparator. So if you put here 2, you will get 4. So 4 times you are getting equal. And what all are the total possible combination? That would be 2 to the power 4. That would be 16. So 16 minus 4 is 12. So 12 times you will get greater and equal. Sorry, 12 times you will get greater and lesser. So half of that will be greater and half of that will be lesser. Are you understanding this point or not? Look, I could have directly written the expressions, but reasoning I am giving. n bit comparator is there. So total 2n bit will be there at the input side. If 2n bit are there at the input side, that means total possible combination of input will be 2 to the power 2n. Now in this 2 to the power 2n, 2 to the power n times you will get equal. 2 to the power n times you will get equal. Why you are getting 2 to the power n times equal? Because this will have n bits. And in n bits, what are the total possible combination? 2 to the power n. From n bits, total possible combination are 2 to the power n. And 2 to the power n combination could be 0 0 0 1 1 0 1 1. In 3 bits it would be 0 0 0 0 0 1 0 1 0 in that manner. So those combination, the same will happen in B0 B1 as well. The same thing will happen in B0 B1 as well. So at that time both will be equal, right? So 2 to the power n times it will be equal. Now whatever is left, what is left? These 2 to the power 2n was the total combination. Out of this 2 to the power n are equal. So this much is left. Half will be greater and half will be lesser. That means in half times A will be greater and in half times B will be greater. That's it. So greater and lesser. That's it. Very easy. Very, very easy. So total possible combination we have written. Right? I hope you have understood the concept here. Okay, so you can just remember this thing. Like no need to remember. I hope you will be understanding it, and in the examination you can directly write it down. Take an example of 2-bit magnitude comparator or 3-bit magnitude comparator. 3-bit magnitude comparator. So in 3-bit magnitude comparator, input will be 6. So total combination will be 2 to the power 6. What that is? 64. 64 combination. Right? Out of these, 2 to the power 3 are equal. 2 to the power 3 means 8 equal. And 64 minus 8. What that would be? 56 by 2. That is 28 greater and 28 lesser. That's the thing. Okay, well and good, very easy. If these kind of questions are asked in the examination, you can tell it. You can tell the final. You can tell these combinations, like how many times it would be greater, how many times it would be lesser. Now, how to write down the final expression? So that we will see now. Let's write down the final expression for a greater than b. But before that, let's check the conditions when a can be greater than b. So when a can be greater than b. First condition is this, that if your a1 is greater than b1. If a1 is greater than b1, do you need to look at a0 and b0? No. If a1 is greater than b1, then certainly your a will be greater than b. Or what could be the second condition? That if a1 is equals to b1, if a1 is equals to b1 and a0 is greater than b0, then also a will be greater than b. Like if first bit are equal, then this bit should be greater than this bit. a1 is equals to b1, then a and a0 is greater than b0. So if these two are equal, then certainly, if these two are equal, then if a0 is greater than b0, then certainly a will be greater than b. So these two conditions are there, right? And when a can be equals to b, when a can be equals to b, which is a1 is greater than a0, sorry, a1 is equals to b1 and a0 is equals to b0. Both conditions should be satisfied. That's why and is there. Here there is or, here there is and, here and will be there. Why so? Because a1 has to be equals to b1 and a0 also has to be equals to b0. Then only both numbers will be equal, right? You have understood it. Let's write down the expression. So greater expression I need to write. So for greater expression, here I can write down the bits a1, a0, b1, b0. That means a1, if a1 is greater than b1, so a1 is greater than b1. That means a1 has to be 1 and b1 has to be 0. Then only a1 can be greater than b1, no? So a1 is greater than b1. So a1 is 1 and b1 is 0. Or if a1 is equals to b1, if a1 is equals to b1. Now when a1 can be equals to b1, when a1 can be equals to b1, that a1 is 0 and b1 is 0, or a1 is 1 and b1 is 1. This I have written a1 is equals to b1. This I have written a1 is equals to b1. Here also you can see what was your a0 equals to b0, that was XOR gate. What would be your a1 equals to b1, that would be your XOR gate. So this I have written a1 is equals to b1. So let's write down this is what I am writing. a1 is greater than b1 or a greater than b and a0 greater than b0. So a0 is 1 and b0 is 0. So that would be the final answer. Let me explain it again. So what all are the conditions of greater? So first we will start with the MSB bit greater. So if a1 is 1 and b1 is 0, if a1 is 1 and b1 is 0, or if a1 is equals to b1, so if a1 is equals to b1, when it can be equal, a1 is not there and b1 is not there. Not there means 0. a1 is 0 and b1 is 0, or a1 is 1 and b1 is 1. So in both of the conditions, let's just say this 1, this 0, this 0. In both of the condition, a1 and b1 would be equal. a1 and b1 would be equal in both of the condition. In this condition as well, in this condition as well. Then what is the other condition? To be greater. So this is if they are equal and a0 is greater than b0. a0 is greater than b0. That means a0 is 1 and b0 is 0. Are you getting this point or not? I hope you are understanding it. Let me explain it once again. We are writing for greater. So that means MSB bit should be greater. This is the first condition. If that is happening, then it is fine. There could be other condition as well. So first I will write down the first condition, that if A1 is greater than B1. So if A1 is 1, dot B1 is 0. A1 is 1, A1 is there, dot B1 is not there. Or what could be the condition? That if A1 and B1 are equal. So what is the condition for A1 and B1? A1 XOR B1, A1 XOR B1. So if A1 and B1 are equal, that means A1 is not there and B1 is not there, or A1 is not there and B1 is not there. This is the condition for A1 is equals to B1. Now what could be what we require? So if A1 is equals to B1 and A naught should be greater than B naught. So A naught has to be there and B naught should not be there. I hope you are understanding it. I am taking the examples as well. Can you write down this one? Here B is greater than A. So how will you write down? B is greater than A. First condition could be that B1 is there and A1 is not there. B1 is there and A1 is not there. What could be the next condition? That if A1 is equals to B1, A1 is equals to B1. So A1 is equals to B1 could be if A1 is 1 and B1 is 1, B1 is 1 and A1 is 1, or B1 is 0 and A1 is 0. So if A1 is equals to B1 and B naught is greater than A naught. So that's it. This is the final answer. This could be written as B1 A1 bar, B1 XOR A1, B naught A naught bar. So I hope I have explained it clearly to you. Let's write down for the equal one. Here as well you can write A1 is there, B1 is not there. A1 and B1 are equal, that means A1 XOR B1. A1 is equals to B1, that means A1 XOR B1. A naught is there and B naught is not there. Let's write down for equal. When they will be equal? A1 is equals to B1. So what do we write for A1 equals to B1? A1 is equals to B1 and means dot A naught is equals to B naught. Equal means dot. That's equal means XNOR gate. For 3-bit magnitude comparator, try writing down the final answer. For 3-bit magnitude comparator, what would be the first condition? That A2 is there and B2 is not there. A2 is there and B2 is not there. Or if A2 and B2 are equal, then A1 is there but B1 is not there. Or if A2 and B2 are equal, A2 and B2 are equal and A1 and B1 are equal, then A naught is there but B naught is not there. That is the final expression. Are you getting this point? A2 is greater than B2. So A2 is there, B2 is not there. Or A2, B2 are equal but A1 is greater than B1. So A1 is there, B1 is not there. Or A2, B2 is equal and A1, B1 also equal. And A naught is greater than B naught. That's it. What it would be for equal? For equal it would be A2 and B2 is equal and A1, B1 equal and A naught, B naught equal. For equal, XNOR gate. Equal means XNOR gate. That's it. What about B greater than A? So if B3 is there, and A3 is not there. If B3, A3 are equal, that means B2 is there but A2 is not there. If B3, A3 equal and B2, A2 equal as well, then B1 is there and A1 is not there. So this is the condition. Right? So that's how we write down the final answer. Let me explain it one last time. Here I will explain again. Okay? That A1 is there, B1 is not there. Or A1 is equals to B1. A1 is equals to B1, then we will compare A naught and B naught. So if A1 is equals to B1, how it can be written in XNOR gate? A1 XOR XNOR B1. How I can write A1 equals to B1? A1 equals to B1 would be when A1 is there and B1 is there, or A1 is not there and B1 is not there. So A1 XOR B1, and A naught should be greater than B naught. That means A naught is 1 and B naught is 0. So A will be greater than B if A1 is greater than B1, or if A1 is equals to B1, A naught is greater than B naught. That's it. If A1 is equals to B1 and A naught is greater than B naught. So this is how you can say. For 3-bit, how you can say that A2 will be greater than B2, or A2 is equals to B2 and A1 is greater than B1, or A2 is equals to B2, A1 is equals to B1 and A naught is greater than B naught. In that manner you can proceed. So you can write down the final expression of any bit comparator, right? So they can ask these kind of questions in the examination. So there you will not be doing this analysis. This analysis are just to tell you that number of possible combinations. So n bit comparator is there, 2n bit will be at input, 2 to the power 2n will be total combination, 2 to the power n would be equal, 2 to the power 2n minus 2n by 2 would be greater, and 2 to the power minus 2n by 2 will be lesser, right? Proper reasoning also I have given. Why is that happening, right? Now you need to make a 2-bit comparator from 1-bit comparator. So try doing it on your own. Think about it. You need to make 2-bit comparator with the 1-bit comparator. So these outputs you are already having. Think now. So what I need to make, let's write down the final answer. This is what I need to make. Final answer would be, better I should show it here. So this would be my final answer, that 2 bits A and B, sorry, not 2 bits, 2 values will be there, and finally you will get greater, equal and lesser. So A will be there, which is a string of A naught and A1. B will be there, which is a string of B1 and B naught. This is your 2-bit magnitude comparator. And greater you need to find, equal you need to find, and lesser you need to find. So greater, that is A greater than B. How I can write? How I can write? What this shows? This shows that A1 is greater than B1. What this shows? That A1 is equals to B1. And this shows that A1 is less than B1. What this shows? That A naught is greater than B naught. This shows, what does this show? A naught is equals to B naught, and this shows A naught is lesser than B naught. And what is my input? Input is A1 A naught and B1 B naught. So if I need to write greater, that is A greater than B, how will I write it? How will I write it? That if I get G1, that means A1 is greater than B1, it's all over. If A1 is greater than B1, then certainly A is greater than B. Or if A is equals to B, A1 is equals to B1. If A1 is equals to B1, then A naught should be greater than B naught. So this is GA greater than B. Are you getting this point or not? Did you understand what did I do here? A1 is greater than B1. So this output will say that your A1 is greater than B1. So if this output I can take, or if both are equal, if A1 is equals to B1, then at least A naught should be greater than B naught. That means this G naught I need to pick. So that would be your final G. Is there any other condition? If I take this one, that I am having L1 first, that means A1 is less than B1. So certainly that if A1 is less than B1, that means certainly B will be greater than A. There is no chance, we cannot think of anything. If MSB bit is greater, that means certainly the number will be greater. So that is the condition for GA greater than B. So better I should write here. I will again write it here. GA greater than B. What is that? That first you can get A1 is greater than B1, or if A1 is equals to B1 and A naught is greater than B naught. What about GA equals to B? What would be that condition? A1 should be equals to B1 and A1, A naught should be equals to B naught. What about GA less than B? So B1 should be greater than A1, or if B1 is greater than A1, all over. Or what could be the condition? That if A1 is equals to B1, then at least B naught should be greater than A naught. B naught should be greater than A naught. So that's the final expressions. So these are the final expressions, right? I am assuming that this is my MSB and these are my LSB. This is the assumption we have made. So now if I need to implement it, so how will I implement it? Eventually I need a XOR gate. In that XOR gate, this input is going E1 dot G naught, E1 dot G naught. E1 dot G naught. What about this? This is G1. So what you will get here? You will get this G, that is G1 plus E1 G naught. For equal, what you will do? For equal, E1 dot E2. That is E1 dot E2. This will be your equal. For lesser as well you can make the same thing, you can make for lesser as well. Okay, so that I am keeping for you. So this is, you are making 2-bit comparator from 1-bit comparator. Let's try make. Now let's make 3-bit magnitude comparator from 1-bit magnitude comparator. So this you should do on your own. So what you need to find, this is your A, which is A2, A1, A naught. So for A2, B2 bit and B is B2, B1, B naught. So for A2, B2 bit you have made 1-bit comparator, 1-bit comparator, 1-bit comparator. A2, B2, A1, B naught, sorry, A1, B1 and A naught, B naught. First, let's find greater. Greater means A is greater than B. So when A can be greater than B, if initially only you get A1 is greater than B1, sorry, A2 is greater than B2. If initially only you get A2 is greater than B2, or if both are equal, A2 is equals to B2. If both are equal, first bit is equal, MSB bit is equal, and A1 is greater than B1. First bit is equal, but the second one is greater. So into G1. If MSB and the next bit is also equal, that means this bit and this bit is also equal, then this should be greater. I mean, A naught should be greater than B naught. So this is the condition of greater. What about the condition of equal? Equal condition would be A2 is equals to B2 and A1 is equals to B1 and A naught is equals to B naught. What would be the condition for A less than B? A less than B means B should be greater. So what does this shows? That your B is greater. So if I am getting L2 all over, or what could be the condition? If A2 is equals to B2, but A2 is equals to B2 and A1 is less than B1, or you can say B1 is greater than A1. Or if both are equal, A2, B2 is also equal, A1, B1 is also equal, then at least, this was showing equal, and at least this bit, the final bit, the LSB bit should be greater. So B naught should be greater than A naught. So these are the conditions, and this is how you can make it. So G2 you will pick, E2 you will pick, G1 you will pick, make an AND gate and then another AND gate, and in that manner then you will connect OR gate. So in that manner you can get 3-bit magnitude comparator from 1-bit magnitude comparator. So these kind of questions can be asked in interview, And even in the gate examination, they can directly ask the expression that your 1-bit magnitude comparator is there, whose outputs are G2, G1, G2, E2, L2, and G1, E1, L1, and G0, E0, N0. If you are making 3-bit magnitude comparator from 1-bit magnitude comparator, what would be the expression for G? So that would be the expression. So this is how you need to write in the gate examination. And I have given enough intuition to do it quickly. I hope you are understanding it in a better manner now. Okay. Is there anything else? Yeah. 3-bit magnitude comparator from 2-bit magnitude comparator and 1-bit magnitude comparator. Okay. So what you need to find? G. Here what this is showing? This is showing that A2 A1 is greater than B2 B1. This is showing that A2 A1 is equals to B2 B1. This is showing that A2 A1 is less than B2 B1. Now we do not know how they are greater, how they are lesser, but we just know that these two bits are greater than this bit. So if I need to write A greater than B, then if I am only getting G2 all over, if I am only getting G2, then it's all over. Why it is all over? Because 2 bits are greater. Combination of 2 bit is greater than the next one. It could be this condition as well, or it could be this condition, or it could be this condition. But combination of first 2 bit is greater than this bit, which is your A0 B0. So here it is A0 greater than B0. Here it is A0 is equals to B0, and here it is A0 is less than B0. It's all over. If initial 2 bits are equal, that means it is 0 0 0 0. If these two are equal, then at least this should be greater. So if this is 1, this is 0. So at least this should be greater. That's it. What about A equals to B? Initial 2 bits should be equal, and these 2 bits should also be equal. What about A less than B? A less than B. That A less than B, that means B should be greater. So this should be greater. If this is greater, all over. Or if these are equal, then at least B0 should be greater. This is how you will write down the final expression. So without even writing down these outputs, that A2 A1, B1 B2 B1, A1 A2 A1, B2 B1, or A0 B0, without writing down these expressions, you should be able to write down this final expression. That if G2 is there, then all over. Or if E2 is there, then G1 should be there. For equal, E2 and even both should be there. For lesser, if L2 is there, all over. Or if E2 is there, then L1 should be there. This is how you will write down the final expression. And now I hope till this point everything is clear in magnitude comparator. A lot of times I have seen people writing down the final expression using this K map, but we are not going to use the K map. K map here we have never drawn, and this combination also I have drawn just to make you understand that there will be n bit comparator, then there would be 2n bit input, and 2 to the power 2n will be the total combination. Out of these, 2 to the power n will be equal, and rest will be unequal, greater or lesser. So half of them will be greater, half of them will be lesser. Okay, let's take example of 3-bit magnitude comparator. That means 3-bit means there will be 6 input. If 6 input are, that means there are total 64 combination. Out of those 64 combination, 2 to the power 3, 2 to the power 3 means 8. 8 will be equal. Now 64 minus 8 will be 56. So 56 will be greater or lesser. So 56 by 2, that would be 28. So 28 will be greater and 28 will be lesser. So this was the important point. And what was the other point? You just need to write down the output. When it will be greater, A1 is greater than B1 all over, or A1 is equals to B1 and A0 is greater than B0. So A0 in dot B0 bar. And when they will be equal, all bits are A1 B1 should be equal and A0 B0 should be equal. So A1 is equals to B1, A0 is equals to B0. Okay, and in that manner we have written the final output. So I guess, yeah, that's it about this whole video, and I hope this concept is crystal clear to you. In the next video, we are going to study about multiplexer. So let's start studying about multiplexer now. Yeah, hi everyone. So just a small correction. I did a blunder here, that this I did not notice actually. A1 is the MSB bit, no, and B1 is the MSB bit. So those should be the MSB bits. A1 and A0 and B1 B0. This is how it should be written, because your A was A1 A naught and your B was B1 B naught, and in that manner only we have wrote these expressions. A1 A naught greater than B1 B naught, A1 A naught equals to B1 B naught. In that manner only we have written that A1 is greater than B1. So that was a blunder from my side, I just noticed it. Okay.